All right, can you see my slides?
Yes, but there's
Yes.
Yes? No?
Yes, I can see it.
Hello? It's odd, I can't hear anyone. Hello?
yes, I can see.
We can hear you.
Okay, thank you. God. Why? All right, sorry for the trouble. So let's get started from a quick introduction what Trie is, what problem does it solve. So put it short, it solves, given a set of strings, how to quickly find out if any input string exists in the set. And here I gave an example, a set of words, and then example query, which is to answer if the word try is in this set. Well, as the simplest way to put it would be to create just a list, and then when query, you enumerate through the list, and which is, as we all can imagine, quite slow. And what try does is a definition from Wikipedia. So it turns the word set or the string set into a tree structure. So this example set can be turned into this tree structure when, for example, we need to look up a word to. It tries to go through the edges with with labels to the next letter. So here it goes to the left, goes to the T node, and then goes to with searching the O, goes to the to node. So if we want to search the word try, we go to it. It will go to the first loop, virtual loop, and then goes to the next node because it's a T, but T has no outgoing edge with R labeled. That means the word doesn't exist in this set, so it can quickly return. In this case, we compared only just 1 byte, 2 bytes, right? First to look up T, and then try to look up the R, 2 lookups. Then we can return it doesn't exist. So what does try mean for mqtt? Well, mqtt topics are a word segment of words split by the slash symbol. In this case, we have three topics. We can build this tree like this. The main difference is that comparing to the typical try use case, it's that the nodes are words, but not the letters. For example, foo itself is a node. So if we want to look up a foo bar topic, a foo plus bar topic, then we go through the most branches of the tree to reach the leaf node, which means there is a hit. So before 4.3, how does EMQX look up a given topic? For example, it's the same tree as the previous slides. If we have a full something bar topic coming in, if there's a message being published to this topic, then we go through the tree like this. First, it goes to the virtual root node, realizing to find out that there are more than 0 edges. So it can continue. It tries to match the hash topic not found, and then plus not found, and then it finds the foo node, goes to the right, and then it looks up the foo's edge, looks up the edges, foo hash and the foo plus, to find there's a node from foo with label plus to foo plus, and then it goes deeper, right? And finally it reaches the foo plus bar topic filter. And of course, it needs to go up in the stack again to search for foo something, realizing that there's no outgoing edge from the foo node with something in the edge label. Then it's not. Then we can stop here. Internally in the code or in memory, since the mqx is implemented in Erlang, we can take advantage of the edge tables to store the tree structure. We have a node table and then we have an edge table. And it's almost like a direct mapping from this tree structure to the table structure. It's only not, it's just not as straightforward as the tree structure. So it has from the edge table, it has a from node, the source node, and with a label on the edge, goes to the destination node. So taking the rightmost branch, for example, from root, it goes to this edge, foo, with label foo, goes to the node foo. And then from here, it goes to the node table foo, node with label foo, has a plus edge, goes to the foo plus, and foo plus goes back to the node table, and then foo plus with an edge bar goes to the foo plus bar node. If we take a closer look, we can easily find out that, or maybe not as easy. If we think again, the front, the source node and the two nodes, they are only this node table consists of all the nodes from the source nodes and the two nodes and the target nodes, right? So this information is actually redundant. We don't really need them. Yeah. Do we really need the edges? This is another question. The answer is actually no. So in 4.3, if we don't configure compaction, I will get into the compaction details later in later slides. The data structure has changed into this two logical tables, but actually they're internally stored in the same table, but only with a different tag. So all we need to store is actually the prefixes and the topics. Then the question is, oh, and also we have deleted the virtual root node because there's no need for it. And no more edge information. Then the question becomes, how can we search such tables when an updated version would be to the same input? So foo something bar, it can try to look up the hash, not found plus not found. Then it tries to look up foo as a key to find out that there is a prefix having counter greater than 0. So it can continue to try to match foo hash and foo plus. So foo hash not found, foo plus find there's 1. And then it tries to match The next level is hash and plus. Nothing can be found on here. And then finally it finds a topic with foo plus bar. And of course it needs to go back up in the stack again to search for foo something. So there's no such topic having such prefix. That means we can stop here. Is it clear enough? So to put it simple, edges are not stored in when inserting the topics or prefixes, because they are computed. They can be computed from time when searching. It's a compute time. It's a runtime information rather than static information is stored in database. So taking it to the next level, we don't actually need to store the topics without wildcard level as a suffix. So in this case, we can delete A, AB, foo. We only need to store A plus and foo plus. And the topics are the same. So we still need to store them. So how does it work? How does the search work in such case? If we try to try to delete all the prefixes without a wildcard suffix. Well, the search becomes a bit more complicated, but so to put it short, it tries to enumerate all the possible wildcard positions. So to go to as a full flow, it tries to search for hash from the start and then plus, and then try to find. The next level would be using hash or plus to replace the something level. Nothing to be found, and then try to find foo plus bar. Foo plus there is such a prefix, and then it tries to go to find the next level with plus replacing something, and then we can look it up again to find out there's a topic. And the difference is here. If it tries to look up foo something, there's nothing to found here, and you'll try to still need to go deeper into the stack or search in the deeper in the tree. Of course, there's nothing to be found. So these three operations are wasted in this specific case. So the disadvantage of compaction, the advantage, of course, obvious, because we don't have to store the prefixes. The tables can be quite compacted, a lot less memory consumption. Sorry. The disadvantage, of course, is that the search space is a lot larger. So to put it, so for any publish, you don't have to look up level times 2 plus 2 times in the trie table. Here's a simple enumeration of all possible searches. Does it worth it? We will have to benchmark to find it out. So this is some very recent benchmark that I did. So some background. This trie compaction feature was added in RC5. So I took RC4 as the baseline to compare. And in and in 4.3.0, we have changed the table type, the X table type, to ordered set in order to compare the old behavior. I've changed the type to set just to compare if the algorithm is better or worse. So here in RC4, so I've tested 80,000 wildcard topics, 8,000 subscribers and 10 topics each, 80,000 publishers with 100 lookups each. In 4.3 RC4, it consumes 109 megs of data in the Trie tables. With no compaction, it's 46. And with compaction, it's just about half of it. And then the lookup cost is 40 milliseconds for each client to look up. So remember, the clients do 100 times lookup, and then the time is divided by 4, by the number of lookups. So the latency is 40 milliseconds, and with no compaction, it's more or less the same. With compaction, it oh, sorry, I think I put it wrong. It should be here. 10, 44 is here. Oops. And more interesting numbers is actually the insert latency. In 4.3 RC4, it takes 3.6 seconds to insert, and with no sorry, again, I missed it. I put it in the wrong order. Here it's 1.3 seconds. With compaction, it takes just 280 milliseconds.
I have a question. Why it says per client average? Or is that in total? Those 3.6 seconds for 8,000 subscribers.
Could you repeat?
Yeah, go back to that table.
Yes.
Yeah, it says per client average values. Is that per client or
It's per client, per airline process. Sorry.
It's process. Okay, because it says per client, I was thinking it's like one subscriber takes 3.6 seconds. That's
yes, that's one client. That's one. That's I spawned in my local test. I spawned 8,000 subscribers. They do 10 topics. They subscribe to 10 topics each in this pattern.
Okay.
And for each, it takes 3.6 seconds. That means it takes like about 36 seconds for one subscriber to finish. But in total, but they're running concurrently though. So 8,000 subscribers, they are all running concurrently. I forgot about the total time it took.
Okay.
With compaction, it's a lot faster. With compaction, and one thing to note is that I changed the table to from ordered set to set, just to compare the algorithm's behavior, but not the tables to affect the test result. By default, so we have changed to ordered set, because we believe that with massive size of the data, the performance of ordered set will be better than the sets. We'll need to test it more in a more serious load test. And then here's a very early real stress test in a 3-node cluster setup with 8 cores, 16 gigs RAM each, 4,000 subscribes per second. That's controlled from the client's behavior. As we can see that it's steadily maintained at this level, and the response time is less than 10 milliseconds. So it takes about 8 minutes to accept all 2 million subscribers. Sorry, 8 minutes. So I'd like to mention some best practices, especially when compaction is used. We should try to avoid sharing prefixes between the subscribers. A good example is try to use the client ID because it's unique before the plus sign in the topic, in the wildcard topic. A bad example is, of course, after it. And then we should also try to use topics with less levels. One abuse of that mqtt topic would be to just because it can, so we just we use mqtt topic for application namespacing, which is not a very good idea. So a good example is to if you have a namespace, continue using a dash or dot for the namespacing, but do not try to turn it into like mqtt topic with slashes. So summary, Trie compaction is made by default. Is made default in 4.3, and to change it, I can set this environment variable or just change the mqx.config. And there will be more performance improvement presentation from William. If any questions, I can take it. By the way, kudos to William for the Trie compaction idea.